Good afternoon or good morning, depending on where you're calling from today, and welcome to the most recent installment of the Remediation and Risk Management webinar series. Today's topic is 20 years in the field, updates to Hawaii's decision unit and multi-increment sample guidance. I'm Mike Gurney. I'm with Eagle's Environmental Support Division. I'm going to introduce our presenter, Roger Brewer with Hawai'i Department of Health, Hazard Evaluation and Emergency Response Office in just a second, but I've got a couple quick intro slides here I want to cover as we get started. First, a quick thank you to our partners in this webinar series, the American Institute of Professional Geologists, the Michigan Association of Environmental Professionals, and the Air and Waste Management Association. For today's webinar in particular, keep in mind we are recording this webinar, so keep an eye in your inbox over the next couple days. I will send an email with some follow-up stuff as well as a link to this recording. If you have colleagues that they know they registered but they weren't able to attend today, let them know. I will send out that link in the next few days. All lines are muted during this webinar, and they will remain muted throughout the webinar. So if you want to engage with us, and we really hope that you do today, use that Q&A box down at the bottom of your Zoom toolbar. We'll have some time at the end of the presentation. We'll be able to use that to go over some questions and hear from Roger more specifically. So with that, Roger, I'll have you turn on your mic, turn on your camera, and let's see if I can stop sharing and let you take it away.
Hey, Mike. All right, thanks a lot. Let me pull up my slides. Good morning, everybody.
And like I said, good morning, good afternoon. Roger, it's bright and early in Honolulu. So thank you for joining us here this morning to give this presentation.
No problem. Glad to be here. All right, I'm going to turn off my video. It sometimes messes up the Zoom calls. Okay, I wasn't sure what to name this presentation. I like the idea of a faster, better, cheaper. So what I want to talk about today is how we incorporated the theory of sampling into environmental investigations in Hawaii. It's spreading throughout some of the other states within EPA, and I'll mention in a minute, I've been working outside of the US and China and other countries also. This figure here pretty much tells the story. There's two different groups of sampling intensive industries. We're looking at particulate matter in particular. It's the commodities industry, where they're looking for mining of gold, copper, other minerals, agriculture, looking at grains. Imagine testing every grain in a wheat field. Recycling all those stolen catalytic converters. I met a group from Germany that makes a lot of money recycling those. And pharmaceutical companies. All these industries here need to determine the concentration of whatever their target commodity is in the mass of material they're testing. Then we have the environmental industry on our side. We're looking at contaminants in soil, groundwater, soil vapor, indoor air, such. Let's see. So we got started in Hawaii about 2004. This is a 4-acre former pesticide mixing area where they used to mix arsenic and they put it in sugarcane fields. And our project manager at the time collected a few discrete samples like we were all doing at the time and started noticing some variability between closely located points. So he started collecting more samples. And the more samples he collected, the more confusing the data got. In this case, he was using a 50-foot grid of samples. He collected over 60. At some point, I think we're pushing 100 here. We turned this into an interesting research site. But you can notice, start looking closely at the numbers. This in ppm, by the way. See a 1300 ppm arsenic right beside a 2.5 ppm. On the other side is a 208 ppm arsenic. So the more he tested, the more random the data got. And it became impossible to prepare some type of iso concentration map. It also became pretty apparent that making these types of maps on discrete data really wasn't reliable. And he also, at the time, we had the lab start testing individual samples, discrete samples of soil at the laboratory. That time, laboratories only testing 1 gram of soil for metals. It's about a pinch. And he saw the same variability within a single sample. So think about that, some implications. That's how we got started. Let's see. By 2007, we had published draft guidance. We introduced the idea of multi-increment sampling and decision units. We'll talk about in a minute. We published the first guidance in 2007. had it out for draft for about 2 years, and consultants were working on it. We published a interim final in 2009, and we've updated that a few times since. The latest update was in July 2023 of this year. I like to refer to this now as risk-based investigation methods. We'll talk about how we start tying in the risk assessors, the remedial experts, and such. Our guidance is in 3 parts. Part 1 is some short fact sheets. These are intended for people who have a few minutes just to get a general idea of what's going on, both consultants, regulators, and also as a fact sheet for responsible parties on different levels of investigation you can do and why you might want to go to a more detailed investigation early on. Part 2 is an overview of the entire process we'll go through in a minute. And that's meant the last hour or two for project managers and management people in office just to get a general idea of the big picture, how this process works. And then part 3 is a whole series of detailed appendices. I think we're up to 17 now. And a lot of the updates we did actually based on some work I started doing in China and about 7, 8 years ago now. And they had a similar problem there. They're in their brownfields, not brownfields, Superfund boom now. It's just amazing the amount of work they're doing. So I spent quite a bit of time over there looking at sites, revising and rearranging our guidance, and also introducing a mega industrial sites, how to investigate those. And that's all reflected in our 2023 update. China just published their first guidance on multi-increment decision unit sampling methods earlier this year. It's terminology, quick as see for, if you're not familiar with the terms, just a decision unit is a simple definition, the area, volume of soil or sediment or whatever, it's not particulate matter, you would collect and test as a single mass if you could. You can't do that, so you collect a representative sample. 2 types of samples used in the environmental industry anyway. First, the discrete sample. That's a sample collected from a single point within a targeted area. You can think of this as a single increment sample. Usually it's about 1 or 200 grams. That's mostly based on laboratory needs. It's not really any science behind the mass of a discrete sample collected. Then we have a multi-increment sample we'll be looking at later. This is a single sample again, but in this case, it's collected from a large number of points within a targeted decision unit area. And the mass and the number of samples included in it, the number of increments included, is based on G's theory of sampling. So this quick outline is, first I'll talk about, like I said, still living in the 1980s. That's when a lot of the environmental guidance was written. One thing, if you recognize the band in this emblem on the upper right-hand corner, probably means you're about as old as I am. And people like me who have been doing this for years and years, discrete sampling methods, it's actually quite a struggle to switch. And as someone said, you're trying to tell me everything I did in the past was wrong. Not necessarily wrong, but it was definitely not very efficient. Then we'll look at the problems with discrete samples real quickly and theory of sampling methods used by the commodities industries and how we can catch up with them. Then we'll go over some case studies, especially to show how these are used in the field, these ideas, and talk about how a transition was implemented in Hawaii. I like The Matrix, one of my favorite movies here. I think this saying by Morpheus puts it in perspective. We always knew, my background's actually a geologist, although I work as a toxicologist for the state here. We always knew something was wrong in the field. We're putting a random handful of dirt in a jar and sending it to a lab, and they're testing a random pinch or handful of that, or spoonful of the soil. So we knew something was wrong. We just didn't have an answer at the time. If I put this figure together, we've basically been doing our own thing since the 1980s. There's 3 groups that are involved in assessing contamination at a site. One group is out collecting samples, another group is testing the sample at the laboratory, and then another group is looking at the data, deciding if there's a potential problem. When out in the field, what's the number of samples you would collect at a site? Well, the typical way to determine this, you take the laboratory budget divided by the cost per sample. That's how many samples you have. You do the best you can. But again, we've always thought out in the field, what if I move that point over a foot? Then would I get the same answer? Probably not. In the laboratory, the smaller the mass of soil that they analyze, the cheaper it is for them to analyze. There's a lot of competition there in laboratories in terms of cost. But a laboratory chemist who actually got us started in doing a lot of our field work, research, was asking the question, like all laboratory chemists would, what if I tested a different pinch of dirt in the sample? Would I get the same answer? Well, guess what? Probably not. And then, the risk assessors are kind of stuck with the data that field people give them. And they basically want more numbers. More and more numbers they get, they think maybe I can get a better statistical evaluation of the data. So everyone's always been doing their things their own way in the past, and the regulators kind of stuck in the middle, wonder what's going on, and just pushing for more sample collection, more laboratory analysis, and talking to the risk assessors. The remediation people have all usually been left out on the side, and very often when they go out to remediate a site, especially if you have a fixed cost type contract, then there's a lot more contamination there than you originally thought. That's a very common thing to happen. And also then you have the responsible parties, the lawyers, the bankers, the insurers, all wondering, where's the endpoint with this? Are you sure it's clean after you tell me it's clean and I buy the property or sell the property? So Dina Crumley with USEPA and I spent a lot of time several years ago. When we were initially working with the ITRC group and their ISM guidance on the origin of discrete sampling guidance. Again, the environment industry is the only industry, sampling intensive industry, that would do this. These are some of the assumptions that we found in some of the earliest documents that set up the method. First one, the level of contaminants in soil or whatever is assumed to be uniform within a contaminated area and zero outside of it. Second, 1985, you're looking at PCBs. 1989, when there's little distance between points, it is expected or hoped that there will be little variability between points. If this was true, then a small number of discrete type samples from single points across the site would be adequate to identify contamination and assess the risk. It also allows direct comparison of individual discrete samples to risk-based screening levels. Again, this approach isn't used in any other industry. The people who put this sampling guides together they didn't do a lot of field work. They didn't have a lot of background in soil, testing soils. I think they were mostly wastewater engineers from what we could gather, where you don't expect a lot of variability. Well, how's that working for you? I've used this slide in a lot of figures, and that's something I always ask myself. The problem with discrete sampling approaches, the need for multiple remobilizations and step-out investigations with no end in sight. It's more the idea, let's go out and collect some data and see what we find. Also, a lot of highly variable data makes it really difficult for risk assessors to make any sense of. And failed confirmation samples, where you, based on your initial samples, the site looked clean, and you collect confirmation samples after excavation, you start finding high concentrations of contaminants again. So you just keep excavating and excavating until your client runs out of money. You run out of time, or they just abandon the site. And then remediated sites later found to still be contaminated. That's something that's started happening probably in the last 10 or 20 years, I would say, where initially cleaned up sites were being resold and redeveloped, started finding some problems. Around, we knew that intuitively there was a problem in the field, and by 2014, 2016, we were well into only using multi-increment samples, decision unit investigation methods. But we were very well funded by US EPA to do field research. In 2014, we undertook a discrete soil sample variability study in the field. We wanted to try to put a number on the variability between co-located discrete samples and also variability in the means based on the large number of samples. So we went to 3 well-known contaminated sites here we had in Hawaii. One was contaminated with arsenic from wastewater. The second, contaminated with lead from incinerator ash mixed with fill material. And the third was known to be contaminated with PCBs from transformer oil. You can see these are all fairly small areas. Each one of these sites, we set up 24 grid points. And at each grid, we collected hundreds of discrete samples, at each one of the sites. At each grid point, we collected 5 co-located discrete samples. We had a laboratory test one of the samples 10 times to look at variability. We also collected multi-increment samples at each one of these sites. And triplicates means we went out and did it 3 times. This is published 2017 paper a critical review of discrete soil sample reliability. Part 1 just discussed the field study results. Part 2 is all the implications, which we'll mention here. This is posted to our web page. Well, we have a couple of recorded presentations posted to our YouTube webpage that goes over the data. Now, the quick conclusion is discrete sample data for a given point are random within a largely unknown range. Any of us that do field work, we always suspected this. Now we can put some numbers on it. At the arsenic contaminated site, the concentration reported of arsenic in a discrete soil sample around any point, on average, varied about twofold. That's actually pretty good. Wait till you see the others. So one sample here, 120 milligrams per kilogram, and then just a foot or two away, 260 milligrams per kilogram. So you see this variability. It's totally random. We're not increasing in any given direction. The lead contaminated site, which I suspect is pretty typical of most sites we work with. Again, this was incinerator ash mixed with fill material. Average total variability between co-located samples is about 7-fold. So one sample here, he sees 120 milligrams per kilogram lead. And then I think we're using 3-foot grid here. But another sample just a few feet away, 800 milligrams per kilogram. Coincidentally, our office, we use a lead screening level of 200 ppm for residential sites. 23 out of 24 points at this site, we could find a discrete sample had a concentration below 200 or above 200. So imagine dealing with that when you're trying to identify areas of contaminants that are of concern. PCB site, PCBs, they're just infamous for being a total mess, trying to characterize them with discrete samples. Average total variability between sample discrete co-located samples, 39-fold. This was the worst point we had. One sample was 4.9 ppm, and then another sample a foot away, actually less than that, 2,400 ppm. This is what causes all the problems we see in the field. With the PCBs, we got a microscope and looked at the soil in more detail. You could see these little things. They look like Tic Tacs, or if you're from tropical areas, they look like roach eggs that are in the soil. What these turned out to be are PCB-infused tar balls. And this gives you an idea of distributional heterogeneity within a sample. In the laboratory, if the laboratory tests a big scoop of this on the right-hand side, then they might get a concentration of PCBs around the tens of ppm because they got one or two of these tar balls in there. If they test an individual or a smaller scoop or one of these single tar balls, these single nuggets of it's soil mixed with the oil, you might get a concentration of PCBs in the thousands of ppm. If you could zoom in and test the matrix of one of these little soil tar balls, you'd probably get PCB concentration of tens of thousands of ppm. So key points here is, one is soil can't be homogenized. That's a bad language in the testing industry for particulate matter at a laboratory, not to the scale of individual subsamples. So if you collect multiple subsamples, you're going to get different numbers. And then the reported concentration of a contaminant varies with the volume and mass of the soil tested. So that's a key point in the mining industry and these other industries, is it's all about mass. The bigger the sample, the more accurate your data are going to be, more representative of your targeted area. And one thing we were hung up on quite a bit in the past is the myth of these maximum contaminant concentrations. Well, if you think about it, the maximum concentration of PCBs in this particular sample here is 1 million parts per million. If you could zoom in on one of the particles small enough, it'd be, say, pure PCBs. So it's the maximum concentration in any sample at any site is either 0 if it's absent or if it's 100% if it's present. So it's a myth that we have to get away from. And the risk, what we're always looking for in environmental work is the mean. So the risk-based objective is always the mean concentration or the true concentration of the contaminant in some specified area and volume of soil. So that's PCBs. We see the same thing with our arsenic samples. You zoom in, this is an electron microscope, you see these little iron hydroxides that are coated in arsenic. They were absorbing the arsenic from the wastewater. You get one of these little nuggets in the laboratory subsample, you're going to get hundreds of ppm arsenic. If you miss it, you may not find any or very trace amounts. This is what soil contaminants in soil would look like if we could actually see it. So it's not like we would think of with original discrete sample data, it's just, a can of spilled paint. So it's either zero or uniform high concentration. Actually looks more like a Jackson Pollock splatter painting. So you move your point over a foot or two or a few inches, you can get a completely different concentration of a contaminant in your sample. Or I like this picture of spilled milk from this truck. See how it ran down the soil? Well, if you couldn't see this, imagine it was AFFF firefighting foam or something. You wouldn't really be able to see it in the soil, but it would look like this. So you move your discrete sample over just a few inches or a foot or something, you get a completely different number. It's really impossible to characterize something like this with discrete samples. This spilt milk scenario also probably illustrates what contaminants look like in the subsurface. They trickle down from a leaking underground tank or pipeline or something. And it's more of an anastomosing mixture of contaminants than something nice and smooth. This is why we have such trouble in subsurface. So the bottom line here is discrete sample data really aren't reliable, not reliably represented in the immediate surrounding areas or for characterization of sites. This is an experiment we did on our lead site. So contaminated site, we had 24 points. Each one of the points we tested 10 different samples, looked at variability within a single sample. So we could kind of guesstimate the range of concentrations of lead in any given sample around a single point. So imagine one person went out to this site, collected a discrete sample at each one of these 24 points, and they could put together this ISO concentration map you see here. So we pick a random number between the range for each one of those points. In this case, the first point was 165 ppm. And somebody else goes out to the site, go to the same points, maybe they're a few inches off, or they test a different pinch of soil on the same sample. They get a different set of numbers. So you see the patterns here now have changed quite a bit. Of course, we never do this. We only collect one set of discrete samples at a site. You don't really realize how random it is. So you can keep doing this. This is someone going back to the same points, collecting discrete samples and having them tested. You're going to get a different number every time, and you get different patterns. They may look real at first, but if you collected replicate sets of samples, you'd realize that they're highly variable. So in the end, you get a random concentration of lead, for any single grid point, and really the maps we generate can be quite random. This is what causes the failed confirmation samples and why it takes so long to clean up contaminated sites. There's a need for repeat investigations in the field with no clear endpoint. So the problem is your lab data aren't reliably representative of the sample that you sent to the lab, and no lab chemist will ever tell you that it is, that I know of. They basically try to stir a sample. As one chemist said, try homogenizing a sample of soil by sticking a metal rod in it and stirring. All the fines go down to the bottom. They pluck a random gram off the top and test. So the lab data aren't reliably representative of the sample. And also the sample is not reliably representative of the area where it was collected. So this problem really can't be fixed by collecting more and more discrete samples. And you can't be fixed by statistical evaluation of discrete sample data. You can finish a project with this approach. We've all done that. It's just highly inefficient. And in the end, unreliable. It's really difficult to know if you missed anything. The large-scale patterns can be real, just to point that out, using discrete sample data. This is a study we did at another arsenic-contaminated site. The consultant collected 100+ discrete samples, shot them in the field with an XRF. They were just trying to map out an area of heavy arsenic contamination within this is a 9-acre site. They knew it was there somewhere. They were able to do that. This is just screening level data. We don't usually do this at most sites. The large-scale patterns are real. In this zone A, you'll see any discrete sample collected and tested within this type A or zone A area is going to fail our action level. That's pretty easy. It's hard to miss. If you see type C down at the bottom or zone C, any discrete sample collected in that area, it's going to be clean. There's no arsenic contamination there. So you can identify these types of areas with discrete samples. The problem is this type B or zone B type contamination where your discrete sample data range overlaps your screening level, like it did in my lead example earlier. And when this starts happening, you're going to get lots of isolated hot spots and cold spots. So if you've ever gone out with a backhoe, like I've done in the past, and start digging up single sample points, you really have to stop. So you're probably stuck in one of these type B scenarios. where if you tested a different sample a foot over, you would have gotten a completely different concentration number. So that's a site characterization and a lot of problems with discrete samples. Or discrete sample data reliable for risk assessment? Well, remember the example I used for lead, 24 points. When you go out to each one of those points, somebody else goes out and collects a different set of samples. They get a different set of numbers. You're also going to get a different mean. So one thing we did with the data there, we did 20 any random iterations of collecting 10 samples each at each one of our study sites, and then calculated the mean and the 95% UCL. So you can see that for site A, the arsenic, the 95% UCL range from 400 to almost 800 ppm, which that makes it difficult for a risk assessor to make decisions on if your action level happen to be 500 or something. The lead site, again, the calculated range of 95% UCL starts to increase even more. Now it's more than twofold. The PCB site, we could calculate a 95% UCL based on any 10 random samples between 9.4 ppm and over 1,000,000 ppm. That's the way UCLs work. So the point here is the estimated mean using a single set of discrete sample data is random within an unknown range. You really don't know what your error is. And that's what a risk assessor actually works for EPA told me a long time ago. We did what we could with the data they provided us. So it's not the statistics, it's not the risk assessors, it's the data that the field people like myself are providing the risk assessors and the remediation people. There are a lot of early warnings about this. Going way back in 1989, there's one group publishing guidance on discrete samples, another group looking at it and putting out warnings. In this case, soil is a very heterogeneous material. Samples with a very small support, mass or volume, may vary from 0 to very high concentrations, within a single sample between co-located samples. 1989, 1992, another warning, the so-called grab sample, discrete sample, is not really a sample, but a specimen of the material that may or may not be representative of the sampling unit, which today we would call decision unit. Great care must be exercised when interpreting the meaning of these samples. And then Francis Bittard, he's sort of the international godfather of sampling in the mining industry. And this is dealing more with the risk assessors throwing out outlier data. And so a common error has been to reject outliers that cannot be made to fit a statistical model. The tendency has been made to make the data fit a preconceived model instead of searching for a more appropriate way to collect the samples in the first place. If you worked for a gold mining company, you collected a discrete sample that was pure gold, and you threw it out because it was an outlier, you wouldn't be working for the gold company very often, was kind of his main point. So all the data are important. It's these outliers that tend to drive risk. Had the same problem with the soil vapor guidance. I won't get into that. We have some presentations posted to our YouTube station. But the same thing with early ideas of vapor intrusion was that the vapor plume under a slab of a building would be fairly homogeneous. Your quote here from California's guidance: the default vapor intrusion attenuation factors assume that the subsurface vapor plume is reasonably homogeneous. If that's the case, you collect a sample of indoor air at a building. They used to do a 24-hour good sample and then collect a random, say, 1 liter sample of soil vapor from under the building. And the idea was you can calculate a attenuation factor that you can use in future guidance. Well, that doesn't work at all. In reality, the vapor plumes under slabs are also very heterogeneous, definitely not uniform. So a key point here is this negates the scientific validity of US EPA's default 0.03 subslab attenuation factor, among other things, problems there. We published a paper on this in 2014 and also did a field study looking at variability of vapor plumes. And there's a recording posted on our webpage. So think about the implications of all these, just some general ideas about issues with discrete samples. And this is, again, from the Matrix movie. You take the red pill, you stay in Wonderland and find out how deep the rabbit hole goes. It's one thing we've been doing here in Hawaii for 20 years. Again, we're very well funded to do field research. And we've been going out in the field for 15, 20 years now. We're one of the few states, I think, that I know of that has their own field team. I think it's one reason we've moved ahead so much in this. A woman in our office who her job is to look for abandoned, contaminated sites around the islands. She spends 6 months a year doing that, doing research, talking to people, and then we go out and collect samples. We've been able to find out how deep this rabbit hole goes to our discrete samples quite a bit and do our own field research for decision unit matrix, a decision unit, and multi-increment samples. So it's been 30 years of kicking the can down the road, I would say. Again, early warnings from way, way back in the 80s when they first started publishing guidance on collection of these discrete samples. Future changes in EPA policy may invalidate some of the discussions in this guidance. And then especially in 2003, and this was a shock for us to read, Dina Crumley, I think, found this. These were some laboratory chemists who also experienced the field work. We searched for a non-conventional statistical sampling theory that takes into account the nature of particulate matter materials. In 1989, we hit pay dirt, the Pierre G sampling theory for particulate materials. However, we were only moderately successful at transferring this technology to the environmental community. So really, a lot of people have known about this problem for a long time. The main problem in the environmental industry has just been a lack of guidance for incorporating these theory of sampling methods. So we're basically learning from the commodities industry on what they've been doing since the 1950s when it started. Well, I have the same question: is what's the concentration of X in Y? And this based on a paper we published in 2022. It's a conference, International World Conference on Sampling and Blending. In this case, it was in Norway. So the commodities industry, again, they're dealing with similar material with particulate material. In the mining industry, what they're tasked with there is typically 20,000 ton masses of ground up ore, maybe gold or iron or platinum or anything, but they have to calculate a concentration of the target commodity within that mass and to calculate the mass of commodity in that, say, 20,000 tons of crushed up ore. And they have to get it right within plus or minus 5%, which is unheard of in the environment industry. Same thing with agriculture, recycling, pharmaceuticals. Again, in this case, they're using a correct use of decision unit and multi-increment type sampling methods to collect samples. So in this case, a single large sample is collected from multiple points within a well thought out decision unit volume of targeted material. In the environment industry, again, we started off, I think, on the wrong foot in the 1980s, where using the incorrect use of single point, discrete, or grab sampling methods is referred to as population statistical sampling methods. In other documents, they refer to as finite element sampling methods. In this case, multiple samples are collected from single points and independently analyzed. And that's really what's got us into trouble. There's been a lot of books, hundreds of papers written on theory of sampling for particulate matter. It's overlooked by the environment industry. These are just a few of the examples. One of the problems was the original guidance was published in French in the 1980s. And before, it only translated in English, I think, in late 80s, early 1990s. But a lot of books out there on this subject that I never knew to look at in the environment industry for the first 10 years of my career. There's still some new books being published now. If you really want to see how sampling is done of soil or particulate matter in general, then the next World Conference on Sampling and Blending, it's held somewhere in the world every year. I've been to the ones in Beijing and last year in Norway. The next one's going to be in Johannesburg, South Africa. You want to meet some sharp folks there. You get paid a lot of money to tell you how many kilograms of gold are in crushed up ore, and they'll be at this conference. I'm going to go if somebody pays my way. Some references for a theory of sampling, if it's termed in those industries. One is the Association of American Feed Control Officials, but really this is used by the food industry in general. It's a document called Good Samples, Guidance on Obtaining Defensible Samples. It sets up the whole process. We'll talk about decision units and multi-increment sampling. And they've got one for the field, the first one, the second one's for the laboratory, good test portions, guidance on obtaining defensible test portions. Kim Espensen from Denmark just published a book a few years ago called Introduction to the Theory and Practice of Sampling, a focus on particulate matter again. It mostly deals with the mining industry. I think it does touch on the environmental industry. If you really want to know about the theory of sampling and the statistical basis behind it, then Chuck Ramsey teaches it's a 4-day class, Introduction to Sampling Theory, Multi-Increment Sample, Site Investigations. And then I think I took his first class in 1990s, didn't really quite get it at that time. I've taken it multiple times since then. He does provide training support after you take his class. And I was working in China in 2019, and the Chinese actually brought him there, taught some classes. They've since redone their sampling guidance. And then again, we have lots of recorded field studies on our webinar webpage. That was really the missing link here. Yeah, it's not so much collecting the samples, in my opinion. What we were missing between the people in the field, the people in the laboratory, and the risk assessors, this whole concept of decision units for sample collection. So again, a decision unit is an area and volume of media you would send to the laboratory as a single sample for testing if you could. We've always thought about these even when we're doing discrete sample collection. So we have exposure areas where we're going to assess risk. It could be playgrounds, or it could be commercial areas, or areas where people are working in general. So these are used to assess risk again. And then the other type of decision units we look at are source areas, or where we think could have concentrated contamination. And we focus in on these areas in our work so we can optimize remediation, isolate the remediation, and try to take care of it as quickly and cheaply as possible. So again, not new ideas of areas to look, but the idea of including that as a single volume and area of soil for testing is kind of new. We also have source area boundary DUs. We try to find clean areas around contaminated sites. Subsurface decision units, same thing as surface, is just soil on top you have to go through to get to. And then sometimes we're stuck with just testing in individual pits and trenches or borings, and we call these exploratory DUs. So again, not new ideas in general, but now we're focusing on a specific volume and area of soil. So how do you even get started with this? So in section 3 of our update, we go through the systematic planning overview. And one thing to keep in mind, in our work here, is only 2 reasons to collect a sample. One is to assess risk. The other is to optimize remediation. So there's 2 different types of decision units there. But we go through a very systematic stage, a lot of upfront work before we go out in the field. First, we state the problem. You draft your conceptual site model, but especially come up with investigation questions. We'll look at some examples of those in a minute. Identify your objectives and determine your contaminants and potential concern. It's nothing new. Identify data needs. We need to go out and collect samples and uses. A big thing is we define decision units. So we're going to go out in the field and specify the exact area and volume of soil, or it could be sediment or whatever we want to test. We develop decision statements. So once we collect the samples, have the data, this is what we're going to do. If the concentration is above X, then we're going to do this. So we decide this up front instead of just going out and collecting data and see what we find and then decide. And then we go out and collect the samples after this upfront work, and we evaluate what the data quality are, usability of the samples. And then we identify potential hazards, refine our conceptual models, and assess risk. All that is typical, but it's the decision unit part that's new. Section 4 of our TGM, then we go into up to 17 appendices now. We look at the site investigation and design implementation. And again, the first part is just some simple fact sheets. We go through conceptual site models. And then we'll look at this in a minute. Example decision unit designation schemes. How you split a site up for sampling in the first place. There's an appendix on theory of sampling, use and misuse of discrete sample data, and then how to collect samples of surface soil, subsurface soil, excavation, stockpiles, how to deal with VOCs, sediments, processing laboratory and processing samples in laboratory, collecting replicate samples. We never really did discrete sampling methods, so we ignored if we did, and how to review data quality. And then some other notes on general field operations, just tips, lessons learned in the field, how to deal with regulations like TSCA and such. These are all detailed in the appendices, so go to as needed. So just moving into some just examples now of how this whole process works. So the first part with the systematic planning, let's say here using apples as an example, it's steps 1 and 2, you prepare a draft conceptual site model and formulate investigation questions. So does the concentration of contaminant X in apples, or we could be talking about soil, pose a long-term chronic health risk? Steps 3 and 4, identify your data needs and designate decision units. Let's say we're looking at these green apples, maybe the red apples here in the middle. So you would first designate your decision unit, and then you're going to determine the representative concentration of contaminant X in those apples, or it could be X in this soil in one of these decision areas here. Then develop a decision statement. If the concentration of contaminant X, the DU exceeds action level, and the media must be disposed of. They're pretty simple. So apples, dirt, it's the same type of process. The next thing we do is collect a representative sample from those apples or from that soil or biosolids, whatever you're dealing with. And here we have this in our guidance on first how to go out and prepare sites and demark or note your decision units, then how to collect soil samples in different types of soil, hard, compact soils, loose soils, subsurface soils, also excavation, stockpile, sediment, sampling of VOCs again. A lot of details from 20 years of experience in the field. It's compiled from consultants in Hawaii and also from consultants in the U.S. mainland and other places. And then we get into discussion as you collected a representative sample from those areas. How do you process it laboratory? The lab just doesn't, they don't open your bag or jar at this time and take out a random pinch or try to stir it. They're going to air dry the sample if it's not VOC, spread it out, and then collect a subsample from that, from say 30 points within that spread out sample, or use the sectoral splitter would be ideal to collect a subsample for testing. We talk about minimum masses. There's a lot of science behind this in the mining industry. Ideally, you want to test at least 30 grams of material in any sample that's been on ground. If you're doing it, collecting it manually, sectoral splitter, maybe 10 grams. If you grind it, ideally you want to test at least 5 grams. That's really not practical at this point. 30 grams isn't, but labs can do 10 grams, for metals and anything else if you talk to them. They may charge you a little bit more. They can do that. That's discussed in more detail in the guidance. How do you know the laboratory got their subsample right? You have the laboratory test 10% of the samples 3 times, compare the data, look at the precision. In the field, you're doing the same thing. In the DUs, 10% of the DUs, you're going to collect 3 different independent samples, compare the data to see how well you're doing, the precision of the data. Then you're going to review the data quality. And we have a checklist here you work through. So first you start at the beginning where the DUs appropriately designated, where the samples collected properly for VOCs or non-VOCs, where they process properly in the field or in the laboratory. Did the laboratory meet minimum mass of the subsample they need to test? With their laboratory replicates, the precision okay, and the field replicates, precision okay. Once you get through all this, then you look at data validation for the laboratory, which, was the equipment running properly? That tends to be what we focus on. You look at data quality, but that's one of the last steps you look at. First, you make sure the samples were collected for properly in the first place. So that's a very quick overview of it, the whole process. So what we're trying to do now is in this 21st century is to work together up front on these environmental projects. So you get your people, your field people, your risk assessors, your remediation experts, your attorneys, your bankers, everybody in the room at the same time, at least involved in coming up with a plan to test a site. So maybe your field person is saying, here's a map of DUs for sample collection. And the risk assessor wants to make sure they have triplicates samples in 10% of the DUs. They can look at precision. The remediation people are saying, wait a minute, I know these DUs are okay for assessing risk, but let's make them smaller so we can isolate contamination, save money on cleanup. And you're also talking with the lab at the same time to make sure they're familiar with processing samples. So doing this all together at one time makes it much easier for the regulators and for everybody else involved. That's what this whole process theory of sampling does for us. In Appendix C of our guidance, we go through, it's really a compilation of 20 years of experience at all kinds of sites, especially focusing on decision unit designations. How do you split up a site to test? And sample collection is a logistical issue in the field. There's one way to collect samples. You have to work it out in the field best you can. So we have examples of commercial industrial sites. You see here, single family home, residential areas, high density housing, schools, large single use areas. We did a lot of agricultural field work and golf courses in the past. Tiny areas, small spills around drums and things. How do you test those? How do you deal with subsurface decision units, designate those? And then testing stockpiles, building demolition debris. That's going to be a big issue. The same process applies there. Dealing with large industrial complexes, petroleum releases, testing at gas stations, especially active where you really have to rely on single borings. And then a lot of examples on dealing with sediment. Some of those actually, if you look at them, they're from Michigan. I was talking to people there several years ago, kind of incorporated their ideas into some of the examples here. And what, future additions to this, we'll keep adding to it, excavations or how about some AFFF firefighting foam areas. So I want to end up here, just go over a few examples, give us something to talk about, some discussions to look at this, go back to the Arsenic Hotel, that first site I talked about, and we'll look at how we're doing testing in Maui with some of these pretty tragic fires that hit there. Look at a mega industrial complex and some buried waste pits. So this arsenic site I mentioned before, starting over here, this is one of the first sites we ever applied this decision unit multi-increment sampling method to. Then first we just stop and say, what's the question? Well, this site was going to be redeveloped as a hotel. The question was, does the mean concentration of arsenic in currently or potentially exposed soil pose a potential health risk to future hotel workers and visitors? What's our DU here? In this case, we're focusing on surface soils, and the arsenic was spilled on the surface here. We're also looking at less than 2 millimeter particles. So your particle size is part of your decision unit. Here's what we did at that site. Based on, we actually used the discrete sample data we had, identify what looked like especially heavy contamination in the upper left-hand area, designate that as a spill area decision unit or source area decision unit. The other areas we tried to match up with the planned redevelopment of the site. We refer to these as exposure area DUs, where someone might be wandering around in the site in the future as it developed as a hotel. And then with each one of these areas here, this time we collected 30 increment samples, one 30 increment sample from each area. And then one of the areas, the bottom right-hand corner, we collected triplicate samples. So we collected a 30 increment sample, 3 of those from independent areas, and compare the data. You can see the concentrations we're finding here. This is a pretty hot site. One reason the arsenic is so high in the soil, in a lot of these areas, they used it as a weed killer in sugarcane fields. But there was so much iron in the soil, as soon as they sprayed the arsenic down, the iron would bind up the arsenic and make it essentially non-toxic to plants and even humans in the future. This is a pretty hot site. In this case, the entire site is going to need some kind of remediation. That was the arsenic site. One thing we'll point out here is the mean concentration of arsenic based on our multi-increment samples in each one of these areas was higher than the mean of the discrete sample data we had for each one of these areas. That's something we consistently see. When you only look at a few sample points or points within an area, you're going to underestimate the true mean. The more points you hit within a targeted area, the higher concentration you're going to get because you're capturing hot spots. Here's the assessment of fire impacted areas in Maui. We're working on that. I'll be out sampling next week in Lahaina. So again, primary contaminants of concern, heavy metals, especially arsenic and lead. Investigation questions, we were asked this by the governor to go out and do some testing, is do contaminants in fine grain ash and soot pose a potential health risk to workers clearing fire-related debris throughout the residential commercial areas? And do contaminants and potential airborne dust from these areas pose a potential health risk to residents and school students because they're opening schools adjacent to some of the towns that burned down in the surrounding areas? Those are our questions. So go out into the field, what's our decision unit? In this case, we're looking at the decision unit is all of the fine ash within the residential or commercial areas. In this case, this is Lahaina. It's the Google image after the fire burned down most of the town. So we only have 2 DUs. One is the residential area, one is the commercial area. So our decision unit total is all the fine ash within those areas in general. It's just 1 DU. So we'd collect a single sample from each one of these areas. And in this case, we're planning to collect a 100 increment sample. It's about as high as you ever need to get from the residential area. Ideally, we'd get one from the commercial area, but we're not allowed in there for access for various reasons. And we're going to go to each 100 different house lots within the residential area. And each house lot, we're going to collect 3 scoops of 30 millimeter scoops of ash, combine that all together in a single sample. We already did that. Another area that burned on Maui, it's a small town of Kula, 26 homes burned. In this case, the homes aren't adjacent to each other. They're discontinuous, but still just imagine if the homes were all adjacent. Here again, we're worried about workers, especially going through each one of these areas, clearing out the debris. So it's the same question, it's the same idea. All 8 lots together are the DU, so a single DU, and our decision is the total volume of less than 250 micron ash within these combined burn units. We were given access to 8 of these 26 areas when we went out and collected a sample a few weeks ago. And here's what we found. It was complicated getting the samples. When you show up, there's all this debris. And this stay focused image here is, I did that for myself because it really gets confusing. What should we sample? Are we looking for disposal or whatever? But well, no, the question was, say, would the fine ash in these areas in total pose a risk to workers in the area clearing debris? So again, went out to each one of these 8 homes, collected, in this case, we collected 30 scoops of 30 millimeter scoops of ash from each one of these 8 homes. In this case, each scoop was really representing a single increment. So this is a total 240 increment sample, about 3 kilograms. Submitted to the laboratory for processing. They air dried it, sieved it, tested 10-gram samples for the metals. We looked for dioxins and everything else. Arsenic, 3,193 ppm. It's by far the main risk driver here. It's from CCA treated wood. So that was the burn area. Looking at subsurface now, it's the same idea. You just have dirt over top of the soil you want to test. This was actually a project that I was working on in China at a huge industrial complex. So trenching, when they were starting to do redevelopment work at the site, they found contaminated a former waste pit. So on top, you have a clean layer. Underneath that is some older fill material that looked pretty contaminated. It was kind of greenish in color, solvents and metals and other things. Beneath that, layer C, a lot of waste in here, obviously contaminated. Below that, layer D was native soil, probably impacted by leaching. The soil is kind of turning green and blue in different areas. Then beneath that, a native soil, which we anticipate to be clean. So here we have one area. We could still call it a DU area, but we have 5 different layers, A, B, C, D. We want to get a sample from each one of those. Investigation questions, very similar to contaminants in soil, pose a direct exposure risk or vapor intrusion risk for commercial residential redevelopment, and the contaminants in soil pose a potential leaching risk. In this case, there's a canal nearby or adjacent to the site, and then impacts to groundwater and discharges to the adjacent canal, concerns about aquatic toxicity. So those are our 2 main concerns. Here's how we split up this particular waste pit. It's just a rectangle here. It wasn't quite a rectangle in reality in the field, but the main DU areas, the waste pit itself, then we surrounded it with perimeter, these border area decision units, where we have a feeling that the first ring of decision units here, that 2, 3, 4, and 5, good chance it's going to be contaminated and need remediation. The outer ring, 6, 7, 8, 9, we're pretty optimistic that those DUs, that soil there would be clean. So we've isolated the contamination. And we do the same thing vertically as we did laterally. And vertically, we have these 5 different layers we want to test. And same issue, we're hoping, we know A is probably clean, it's new fill, B, C, and D probably contaminated. Layer E, we're hoping is clean. So we're going to go out here one time, collect a multi-increment sample from each one of these DU areas. In this case, probably a 30 increment sample. And we'll real quickly isolate the contaminated soil and needs remediation, hopefully not need to go back and do any more testing. Then the last example we'll go over
Hey,
here.
Roger, just a quick time check. We got about 5, 6 minutes left. So if you want to zip through your last example here, we got a couple questions.
Okay, so this is the last one
Thanks.
here. So where do you start with all this? Sorry, it's a long subject, but here it's one of the mega industrial sites. When you get started anywhere, and the first thing you start with is one DU. In this case, this was a 50-acre area. There's a site in China again we're talking about. So first we just say, you get your risk assessment people, your mediation people, and your field people together and say, we're just going to call this one DU. In this case, it wasn't acceptable for anybody, remediation for the risk assessment people. So then you start to split it up from there. So we split it up into, in this area, we had industrial operations, another area, residential housing and office buildings. We split it up some, that's better, but still these are too large to collect single samples from in each one of these areas. Just keep splitting it up from that. So now we've broken out individual industrial areas, these manufacturing areas where we know we have a lot of contamination. We split up the housing area into 5 different areas based on the age they were collected. So this is getting better, but it's still too big to collect samples. So we'll split that up even more. Now we split the housing area up based on the risk assessors. They want data for no more than half-acre areas at a time. Now they're going to be pretty satisfied with the housing area. And for the commercial building office area, just 1 DU is probably okay. But these, where they were doing the manufacturing, those DUs are still too big. So now we go to those, each one of these industrial areas and start splitting them up like we talked about before, smaller and smaller DUs to optimize remediation based on suspected contamination. This site, you would just start splitting up a site, then just start with 1 DU. And that's how we did the sites in China, so they can kind of get in, get out. It's a big deal there. They have to get in and get out within 2 years, typically, characterizing and cleaning up a site. So imagine that here. That's it. A few case studies to think about. Hawaii's transition here from 2005, 2009. We had a lot of completed projects. We never went back to look at a site we'd already completed. Some of these properties getting retested as part of a new transition, property transactions. Currently active projects starting in 2009, they could use existing discrete sample data for initial remediation actions. We always required DU MIS data for confirmation. In new projects now, after this long, really no consultants here ever collect discrete samples, anything more than simple field screening. We always start off with decision units, multi-increment samples, and always require DU MIS for confirmation. So that was a kind of a long, quick tour of this. If anybody recognized the Van Halen album cover in the upper right-hand corner, you're as old as I am. Really, again, older. All right, that when we've been doing this for years and years, it's kind of hard to change, but just give you some ideas to think about. Why bother with this? Well, it's better science by far. Fairness to regulated public, time, money spent on cleaning up these sites, give them a clear endpoint, and also just to deal with unforeseen liability of stakeholders and especially consultants. If you're in China, the regulators can be charged with liability issues also. It is competition with other consultants. You get in, get out, get it right. The bottom line here is it really should be a regulatory requirement. It is here. Laboratory data must be representative of the sample provided. Sample provided must be representative of the collection area. So that was it. And thanks for sticking with it. And I'll be glad. I'm not in a big hurry. It's only 7:30 in the morning here if anybody wants to stick around and ask questions.
Great. Thanks, Roger. Yeah, one question right off the bat. Do you mind, can I share this presentation, the slideshow with folks? I know you sent that to me. I can PDF it and share just the slides. Is that all right by you?
Yeah. Yeah, I rearranged some of the slides. I'll send you the final.
Okay. All right, great.
Welcome to do
Yeah,
that.
so look for that along with the link to the recording in the next few days. One question that I had here, and maybe this gets into the maybe the exposure area versus source area decision units, but also
Yeah.
just the scope. I think that the size when this is appropriate.
Yeah.
Thinking that in major cities there's kind of a move to do some urban gardening, and
Yeah.
with just the prevalence of contamination,
Yeah.
kind of throughout downtown areas, is this, we're looking at all the examples were such large scale. Is this an appropriate pathway for something smaller like an urban garden type
Oh,
of thing?
definitely. Actually, some of the first studies we did were in garden areas at the sugarcane mill complexes. And what's the question? Is contaminants, the contaminants in the soil pose a problem for the workers in the garden or for uptake in the produce? So your garden is your decision unit. You go out, you collect one sample from your garden area. We do triplicates just to compare the precision. Use that to assess uptake and also exposure to workers. And we tested produce in the garden also. We do the same thing, for testing eggplants or something. We collect one sample of the eggplant, from multiple eggplants, and we had those tested for arsenic.
Great, thank you. This was a question, you were back on slide like 10, 11-ish. You were talking about YouTube channel and some videos.
Yeah,
Do you know the name of that YouTube channel so folks can go and look those up?
yeah, it's back there. Let's see. There. Yeah, there. If you could, Hawaii's a small state. If you just Google, really the best place to look for Hawaii and then multi-increment samples, and then you'll find our DUMIS webpage.
Okay.
Or you have my email also. Just send an email to me.
Okay, great. Yeah, and I know we're pushing up against the 1:30 mark here, so I want to be respectful of those attendees today. So I will take that there, Roger, as a good segue to say, if you have further questions, feel free to reach out to Roger. Chris Christensen is also on this call here. Chris is a specialist with Eagle's Remediation and Redevelopment Division and a co-lead for our incremental sampling technical and program support team. So if you have questions specific to the state of Michigan, I'd really encourage you to reach out to Chris. And maybe with both Roger and Chris's permission, I will add their contact info to the follow-up email, just so that if you want to continue this conversation, please reach out. We're here to help. So, right, we're from the government. We're here to help. So I want to quick share my screen real quick and just make a plug for our next tentative webinar. Is going to be hopefully on November 28th. So I will send hopefully some lead up information for that. November 28th over the lunch hour, Eagle's updated NAPL characterization, remediation, and management guidance document. We want to share some information on that. With that, I really appreciate everybody coming and joining us today. And again, the early wake up call for our presenter, Roger. So appreciative. Thanks. And like I said, look for those emails from me. And if you have any questions, reach out. Otherwise, we'll see y'all soon.
Thanks so
Okay,
much,
thanks a lot,
Roger.
Mike. All right. Thanks a lot.